For most of human history, reality felt dependable. Events followed one another in a straight line. Causes came before effects. The past stayed behind us. The future waited ahead. And the present was the thin edge where everything happened. Even when the universe revealed its dangers and mysteries, it never questioned this basic structure. Reality existed first. We observed it second. Quantum physics changed that order. At first, the discoveries seemed merely strange. Particles behaving like waves, energy arriving in discrete packets, nothing that couldn't be dismissed as microscopic oddities far removed from daily life. But beneath those early surprises, something far more unsettling was forming. A paradox that didn't just challenge physics, but the very idea of an objective universe. The paradox begins with a simple assumption that events happen whether or not anyone is watching. That reality is a finished story written once, then read by observers. Classical physics is built on this assumption. So is common sense. So is nearly every human intuition about time, memory, and existence. Quantum experiments quietly dismantled it. Again and again, researchers discovered that particles refused to commit to a definite state until they were measured. Not influenced, not nudged, measured. As if the act of observation itself was forcing the universe to make a decision it had been postponing. Before measurement, the particle wasn't hiding a secret answer. It genuinely did not have one. This is where the paradox sharpens. If reality does not settle into a definite state until observation, then what exactly exists before that moment? Not an incomplete version of reality, but something fundamentally different. A blur of probabilities, a menu of possible histories, a suspended state that only becomes real when someone asks a question in the right way. That idea alone is disturbing. But the deeper implication is worse. Because if observation defines reality now, then what happens to the past? If a measurement made in the present determines how a particle behaved moments ago, then causality begins to wobble. Time starts to feel less like an arrow and more like a negotiation. The universe no longer looks like a machine running forward. It starts to resemble a system that waits. Physicists resisted this interpretation fiercely. Einstein famously objected, insisting reality must exist independently of observation. He believed the moon did not vanish when no one looked at it. Yet experiments kept confirming the same pattern. Not once, not twice, but reliably, repeatably, under controlled conditions. The paradox remained. Either reality is incomplete until observed, or our understanding of observation is dangerously flawed. Either the universe is participatory, or the past is not as fixed as we believe. And neither option sits comfortably with the idea of a stable, objective world. This paradox was not born from philosophy. It emerged from data, from detectors, from experiments that worked whether scientists liked the results or not. And once you accept that it exists, the question becomes unavoidable. What kind of universe behaves this way? When observation becomes an act of creation. In everyday life, observation feels harmless. You look at a tree and nothing about the tree changes because of your attention. You read a sentence and the ink does not rearrange itself in response. Observation, in the classical sense, is passive. It reveals what is already there. The quantum world refuses to play by that rule. At the smallest scales of reality, observation behaves less like a witness and more like an intervention. When scientists attempt to measure a quantum system, they are not simply uncovering a hidden truth. They are forcing the system to choose one outcome from many that were previously allowed to coexist. Before measurement, the system exists as a spread of possibilities. After measurement, only one version survives. This is not a metaphor. It is how the mathematics works, or rethink, and more importantly, how experiments behave. A particle can exist in multiple states at once, described by a wave function that encodes all its potential outcomes. But the moment a measurement is made, that wave function collapses. The particle is found in one definite state and all other possibilities vanish. Not gradually, instantly. The unsettling part is that nothing about the measuring device needs to be conscious. A detector, a sensor, a piece of equipment is enough. The universe seems to treat any act of information extraction as a demand for certainty, as if reality itself is allergic to being partially known. This is where the idea of observation crosses a dangerous line, because if observation changes what is observed, then the observer is no longer outside the system. The observer becomes part of the process that generates reality. In classical physics, the universe exists first and knowledge comes second. In quantum physics, knowledge and existence are entangled. You cannot cleanly separate what is from what is known. The act of knowing alters the thing being known. This leads to a deeply uncomfortable conclusion. If no observation is made, the universe does not rush to fill in the details. It remains suspended, unresolved and probabilistic. Reality, at its core, appears to be economical. It does not waste effort committing to outcomes that no one has asked for. Some physicists tried to avoid this conclusion by arguing that the particle must have had a definite state all along and we simply disturbed it by measuring. But this explanation collapses under experimental scrutiny. Carefully designed tests show that no hidden answers exist waiting to be uncovered. The answers are created at the moment of measurement. This is not intuition-friendly. It suggests that reality is not a pre-written script, but a dynamic interaction, a dialogue between the universe and the act of observation itself. And once you accept that observation can create outcomes, a far more troubling question begins to form. What else might observation be capable of creating? The experiment that broke common sense. There is a reason one experiment appears in almost every serious discussion of quantum reality. Not because it is complex, but because it is devastatingly simple. So simple, in fact, that once you understand it, there is no comfortable way to unsee its implications. Imagine a barrier with two narrow openings and a screen behind it. Particles are fired one by one toward the barrier. If those particles were tiny solid objects, like grains of sand, you would expect them to pass through one opening or the other, creating two clusters on the screen. Straightforward, predictable. That is not what happens. Instead, the particles form an interference pattern, alternating bands of high and low impact. The unmistakable signature of waves. Each particle behaves as if it passes through both openings at once, interfering with itself. This alone is strange but still manageable. Waves can do odd things. Then the experiment takes its most dangerous turn when scientists place detectors at the openings to observe which slit each particle goes through. The interference pattern vanishes. The particles now behave like ordinary objects choosing a single path. The mere act of watching forces the particle to stop behaving like a wave and start behaving like a thing. Nothing else changes. The particles are the same. The setup is the same. Only one variable is different. Information. If the universe knows which path the particle took, the wave behavior disappears. If it does not know, the wave returns. Reality itself seems to respond not to physical disturbance, but to the availability of information. This is where common sense collapses, because the particle cannot logically decide how to behave based on whether someone might look later. And yet, that is exactly what the results suggest. The particle behaves as though it is aware of whether its path is knowable. Even more unsettling, when particles are fired one at a time, the interference pattern still forms gradually. Each particle arrives as a single dot on the screen, but over time the collective pattern emerges. It is as if each particle is guided by a structure that does not yet exist, responding to probabilities rather than physical obstacles. Attempts to explain this with hidden paths or secret trajectories have repeatedly failed. The math does not allow it. The data does not support it. The universe is not hiding classical behavior behind a curtain. It is doing something fundamentally different. The double-slit experiment doesn't merely suggest that particles behave strangely. It suggests that reality itself is conditional, that outcomes depend on what can be known, that the universe is sensitive to observation in a way that defies classical logic. Once this experiment was understood, physics lost the luxury of pretending that observation was neutral. The observer was now entangled with the outcome, and from that moment forward, the question was no longer whether reality behaves this way. It was how far this behavior extends. Reality without a witness. Once the role of observation became impossible to ignore, physicists were forced to confront a question that sounds philosophical, but arises directly from the experiments themselves. If observation gives reality its definite form, then what exists when no one is watching? Classical intuition answers instantly. Of course, reality exists. Mountains do not dissolve at night. Stars do not flicker out when telescopes are turned away. The universe does not wait for permission to be real. Quantum theory offers a quieter, more troubling reply. At the quantum level, unobserved systems do not settle into a single state. They remain described by a wave function, a mathematical expression that contains all possible outcomes at once. Not one of them, all of them. The system is not undecided in the way a coin in your hand is undecided. It is undecided in a deeper sense. There is no fact of the matter yet. This does not mean particles vanish when unobserved. It means their properties are not definite. Position, momentum, even our whole existence in a particular state remain unresolved until interaction forces a choice. Reality in this view is not missing. It is unfinished. That idea unsettles people for a reason. It suggests that the universe does not fully commit to its own details unless required to do so, like a story written in pencil, firm only where someone presses hard enough to leave an imprint. Some physicists tried to rescue objectivity by arguing that interactions with the environment count as observation. Air molecules, photons, cosmic radiation, surely these are always watching. In many cases, this explanation works. Quantum systems rapidly entangle with their surroundings, producing the appearance of classical stability. But the deeper problem remains untouched. Even if the environment acts as a kind of witness, the universe still operates on conditional reality. Properties become definite only through interaction. Without interaction, there is no single outcome waiting patiently in the dark. There is only possibility. This leads to a subtle but profound shift. Reality is no longer something that exists independently and is later discovered. It is something that emerges through relationships, through contact, through exchange of information. In this framework, the universe is not a static object but a dynamic process, a system that continuously resolves uncertainty through interaction. And without interaction, it remains open. This raises an uncomfortable implication. If no observer, no environment, no interaction forces reality into a definite state, then there is no single story unfolding behind the scenes. There is a spectrum of potential stories, none privileged over the others. The universe at its most fundamental level appears to tolerate ambiguity, not chaos, not randomness without structure, but a disciplined uncertainty governed by precise mathematical rules, waiting for something to demand clarity. Reality without a witness is not empty. It is pregnant with outcomes, and once you accept that, the next question becomes unavoidable. What happens when the witness arrives too late? Time running backward. If reality becomes definite only when observed, then observation does more than select outcomes. It seems to reach backward in time. This is not speculation. It is the unavoidable implication of a class of experiments that forced physicists to reconsider the direction of causality itself. The most disturbing of these are known as delayed choice experiments. In their simplest form, they resemble the earlier experiments you already know. A particle travels through a system that allows for multiple possible paths. Normally, the choice to observe which path it takes is made before the particle enters. But in delayed choice setups, That decision is postponed until after the particle should have already committed to a path. Common sense insists this should change nothing. The particle must have already done something. The past is the past. Quantum experiments disagree. When the measurement choice is made at the last possible moment, the results still depend on that choice. If the experiment is set up to observe which path the particle took, it behaves like it travelled a single route. If the setup is arranged to preserve interference, the particle behaves as if it travelled multiple paths at once, even though, by classical reasoning, that behaviour should have been determined earlier. It is as if the particle waits to see what question will be asked before deciding how it behaved in the past. This is not a trick of interpretation. The math predicts it. The experiments confirm it, and no signal is sent backward in time in the usual sense. Instead, the structure of reality itself appears non-classical. Events are not fixed until the entire measurement context is complete. Time, in this picture, is no longer a one-way street where causes march forward and effects trail behind. It looks more like a web, where consistency across the whole experiment matters more than chronological order. This deeply troubled Einstein, who saw it as an assault on realism and causality. He believed that events must have definite properties regardless of when or whether they are measured. Delayed choice experiments seem to reject that comfort entirely. The universe does not commit early. It waits. This does not mean the future literally sends messages to the past. It means that the distinction between past and present may not be as fundamental as we think. What matters is not when an event occurs, but how it is embedded in the total structure of observation. From the quantum perspective, asking what really happened before measurement may be the wrong question. There is no hidden footage of the particle's journey waiting to be reviewed. There is only a set of probabilities that collapse into a narrative once observation forces consistency. The past disturbingly appears negotiable, not changeable in the everyday sense, but undefined until the moment it must be defined. Like a story whose opening chapters are finalized only after the ending is written. And if time itself can behave this way at the quantum level, then the question becomes much larger. Is time truly fundamental, or is it something that emerges only when reality is observed? The universe that waits for an answer. By this point, a quiet pattern has begun to reveal itself. The universe does not rush to settle outcomes. It does not insist on filling in every detail the moment something could, in principle, occur. Instead, it behaves as if it is waiting for interaction, waiting for a question, waiting for informations to be demanded. This is not poetic language. It is the most economical description of what the experiments imply. Quantum systems evolve smoothly as probabilities until something forces a resolution. Until then, the universe seems content to remain non-committal, not confused, not incomplete, simply undecided. Reality at its core appears to be conditional. In classical thinking, the universe is constantly doing everything it can, all the time. Every particle has a position, every event has a cause, every moment locks the past into place. Quantum mechanics quietly rejects this excess. It suggests the universe does not finalize what no interaction requires it to finalize. This creates a strange inversion of perspective. Instead of reality producing information, information appears to produce reality. When a measurement extracts a fact, that fact becomes real. Before that extraction, there is only potential. Some physicists describe this as the universe computing outcomes only when needed. Others resist the metaphor, but the behavior remains the same. The universe conserves definiteness. It does not commit to unnecessary details. This idea becomes especially unsettling when you consider scale. At the level of atoms and photons, this behavior is well established. At the level of everyday objects, it seems to vanish. Tables do not blur into probability clouds when unobserved. But this stability is not fundamental. It emerges from countless interactions that effectively force constant observation. The universe feels solid because it is constantly being asked questions by its own contents, but remove those interactions, isolate a system carefully enough, and the strange behaviour returns. Reality softens, certainty fades, possibility expands. This suggests that definiteness is not the default state of existence. It is a negotiated outcome, a product of engagement. And this leads to a deeply uncomfortable realization. If the universe waits for answers, then the questions matter. The way information is extracted matters. The structure of observation shapes the structure of reality itself. This does not imply that human observers control the universe in any mystical sense. The universe does not care who asks the question, but it does care that a question is asked, that information is demanded, that ambiguity is no longer tolerated. Reality, then, is not a passive stage. It is responsive. It responds not to desire or intention, but to interaction, to measurement, to inquiry. Once this perspective is accepted, the universe begins to look less like an object and more like a process, a system that continuously balances possibility against demand. And if reality is shaped by observation at this level, then the next problem becomes unavoidable. What happens when observers themselves are observed? The observer paradox deepens. Up to this point, the role of the observer has been unsettling but manageable. Observation collapses possibilities into outcomes. Measurement defines reality. Strange, yes, but at least there is a clear sequence. First, a system exists in uncertainty. Then an observer measures it. Reality becomes definite. Then a new problem emerged. What happens when the observer is also part of the system? This question is not philosophical abstraction. It arises directly from a thought experiment proposed by physicist Eugene Wigner, known as Wigner's friend. The setup is simple, but its implications are anything but. Imagine a scientist inside a sealed laboratory measuring a quantum system. From the perspective of that scientist, the measurement has occurred. The system has collapsed into a definite state. Reality is resolved. Now imagine an outside observer who treats the entire laboratory, including the scientist inside, as a quantum system. From the outside perspective, no measurement has yet occurred. The lab exists in a superposition of all possible outcomes. Two observers, two incompatible descriptions of reality, both valid according to quantum mechanics. This is where the paradox sharpens into something truly disturbing. Reality is no longer just conditional on observation. It appears to be relative to the observer. For the scientist inside the lab, the result is real. For the observer outside, it is not. And there is no privileged viewpoint that quantum theory can point to and say, this one is the true reality. In classical physics, disagreements between observers are resolved by assuming a single underlying truth. One observer may lack information, but the facts exist independently. Quantum mechanics refuses this comfort. The theory allows multiple observer-dependent realities to coexist without contradiction. This is not a limitation of our knowledge. It is a feature of the theory itself. Some physicists attempt to escape this conclusion by invoking interpretations that preserve objectivity, such as many worlds, where all outcomes exist simultaneously in separate branches. Others accept observer-relative facts as fundamental, suggesting that reality is not a single global story but a collection of locally consistent ones. Either way, the cost is high. If reality depends on perspective, then the idea of an objective universe shared by all observers becomes questionable. The universe fragments into viewpoints, each internally consistent, none absolute. This raises a chilling possibility. When two observers compare notes, their realities must somehow reconcile. And yet, before that comparison, quantum mechanics allows them to inhabit different worlds. Reality in this sense is not just incomplete until observed, it is plural. The observer paradox reveals that observation does not merely create outcomes, It defines which reality is experienced by whom. And once you accept that, the next question is unavoidable. What happens when those realities disagree? When reality disagrees with itself. At this stage, the problem is no longer whether quantum mechanics is strange. The problem is that it appears to allow reality to contradict itself without breaking its own rules. When two observers can legitimately describe the same event in incompatible ways, the notion of a single shared reality begins to fracture. This is not a philosophical exaggeration. It is a direct consequence of treating observers as quantum systems, subject to the same laws as everything else. Recent experiments inspired by Wigner's friend have pushed this paradox out of thought experiments and into the laboratory. In these setups, different observers measure entangled systems and record outcomes that cannot all be simultaneously true from a classical perspective. Yet quantum theory predicts them accurately, and the data agrees. Each observer experiences a consistent reality. The conflict only appears when those realities are compared. This suggests something profoundly unsettling. Reality may not be globally consistent. It may only be locally consistent, stitched together by interaction rather than governed by a single objective narrative. In classical thinking, contradictions signal error. Two accounts cannot both be true if they disagree about the same fact. Quantum mechanics challenges this assumption. It allows for observer-dependent facts that coexist until interaction forces reconciliation. Before observers exchange information, their realities do not need to agree. They are not wrong, they are simply incomplete relative to each other. This forces a radical redefinition of truth. Truth is no longer a universal property of the universe. It is a relational property between observer and system. What is true for one observer need not be true for another until they interact. When interaction occurs, quantum mechanics ensures consistency. The contradictions resolve not by revealing a pre-existing truth, but by enforcing agreement through correlation. The universe does not store a master copy of events. It negotiates coherence on demand. This raises a deeply uncomfortable implication. If reality only becomes consistent when observers compare notes, then before that comparison there is no single reality to refer to. There are only perspectives. The universe, in this view, is not a finished object but a patchwork. A network of interacting viewpoints, each generating its own facts, harmonized only through contact. This does not mean reality is arbitrary or chaotic. The rules governing these interactions are precise and mathematically strict, but they are not classical. They do not respect the idea of an observer-independent world unfolding in the background. Instead, reality appears to be something that emerges between observers, not behind them. Once this point is reached, the conversation inevitably shifts. If reality depends on observation, and observers generate their own versions of it, then what exactly is doing the observing? Is it just physical interaction? Or is there something more fundamental at play? Consciousness enters the equation. For decades, physicists tried to keep one idea safely outside the laboratory: consciousness. Not because it was mystical, but because it was dangerous, difficult to define, impossible to measure cleanly, a concept that threatened to blur the line between physics and philosophy. Yet the deeper the observer problem went, the harder consciousness became to ignore. If observation creates outcomes, and if observers themselves can exist in unresolved states, then what exactly qualifies as an observer? A detector? An atom? A human mind? Quantum theory is precise about equations, but strangely silent about where exactly the boundary lies between possibility and fact. Some early pioneers were willing to go where others refused. They suggested that consciousness might play a role in collapsing quantum possibilities into a single reality, not as a supernatural force, but as the final link in the chain of observation. The point at which information is not just recorded, but experienced. This idea made many physicists deeply uncomfortable. If consciousness is required to finalize reality, then physics is no longer describing a universe that exists independently of experience. It is describing a universe that requires experience to become complete. That implication felt too close to mysticism, too far from the clean objectivity science had fought to preserve. So alternatives were proposed. Decoherence, many worlds, objective collapse theories. Each attempted to remove consciousness from the equation while preserving the experimental results. Some succeeded mathematically. None resolved the deeper question. Because even if a detector collapses a wave function, who or what collapses the detector's state? At some point, the chain of observation reaches something that registers meaning. Something that does not just interact, but knows it has interacted. And quantum theory offers no clear instruction on where that point lies. Experiments do not prove that consciousness causes collapse, but they do something almost as, troubling. They leave room for it. They refuse to rule it out. This has led some researchers to propose that consciousness is not an emergent byproduct of reality, but a fundamental aspect of it. Not separate from physics, but woven into the fabric that allows facts to exist at all. Others reject this strongly, arguing that consciousness itself must ultimately be explained by physical processes. But even then, the problem loops back on itself. If consciousness is physical, it is subject to quantum laws, and those laws do not grant it a privileged, objective standpoint. Either way, the observer problem refuses to stay contained. Reality appears to require observation. Observation appears to require an observer, and the observer cannot be cleanly separated from the reality it observes. This does not prove that the mind controls the universe, but it strongly suggests that the universe is incomplete without experience. And that realization is precisely why this line of inquiry terrified so many scientists, because once consciousness enters the equation, physics is no longer just about particles and forces. It becomes a question about what it means to exist at all. Why? This terrified the scientific world. The fear was never about strange particles or counterintuitive math. Physics had survived those before. Relativity bent time. Quantum mechanics shattered determinism. The scientific world adapted. What made this different was not complexity but implication. This line of inquiry threatened the foundation that science quietly stands on, the assumption of an objective reality that exists independently of observers. If reality depends on observation, perspective, or interaction, then science itself becomes participatory. Measurements are no longer neutral probes of a pre-existing world. They are events that help bring the world into being. That idea destabilizes the comforting separation between experimenter and experiment. For many physicists, this felt like a betrayal of the scientific method. Science is supposed to describe what is there, not what appears because we look. If observation plays a constitutive role, then knowledge is no longer purely descriptive. It is creative, and that blurs the line between discovery and involvement. There was also a deeper fear, rarely spoken aloud. If the universe requires observation to become definite, then what existed before observers? Before life? Before consciousness? Did the early universe wait in a fog of possibility until something emerged to witness it? Cosmology depends on the idea that the universe had a definite history long before anyone was around to study it. Quantum theory, taken seriously, complicates that story. It suggests that the past may not have been fully settled until the present forced consistency. This was not a comfortable thought. Some physicists responded by retreating into instrumentalism, the idea that theories are merely tools for predicting outcomes, not descriptions of reality. Don't ask what is real, they argued. Just calculate what you will observe. This strategy worked practically, but it left the philosophical wound untreated. Others embraced interpretations that preserved objectivity at a high cost. Infinite branching universes, spontaneous collapses without clear triggers, hidden variables constrained or constrained by non-locality. Each solution patched one problem while opening another. What united these responses was anxiety. The observer problem was not just a technical puzzle, it was an existential threat to the worldview that science had inherited from classical physics. If there is no single observer-independent reality, then certainty becomes local, truth becomes relational, and the universe becomes something less like a machine and more like an unfolding process. This fear slowed progress. Discussions were avoided, papers softened their language, consciousness was treated as taboo. The mathematics moved forward, but the meaning was kept at arm's length. Yet the experiments did not stop. Each new result quietly reinforced the same message. The universe does not behave as if it is complete without observation. It does not offer a final, objective story detached from perspective. And the more this became undeniable, the clearer it was why the scientific world hesitated. Because accepting this would mean accepting that science is not standing outside reality, looking in. It is standing inside reality, shaping it by the very act of asking questions. If reality is not fixed, what are we living in? Once the fear settles, a stranger question takes its place. If reality is not fixed until observed, if time is negotiable, if truth depends on perspective, then what exactly is the world we experience every day? It feels solid, predictable, stable. Chairs do not flicker between possibilities. The sun rises without hesitation. Cause still appears to precede effect. On the surface, nothing seems broken. But quantum mechanics suggests this solidity is not fundamental. It is emergent. The world we experience may be the result of relentless interaction. Billions of particles constantly measuring one another. Molecules colliding, photons scattering. Information exchanged so rapidly and densely that uncertainty is crushed almost instantly. What feels like a fixed reality may simply be a reality that is being observed everywhere, all the time. In this view, the universe is not a static structure. It is a continuous negotiation between possibility and constraint. Where interaction is dense, reality hardens. Where interaction is sparse, it softens. This reframes existence in a profound way. Reality is not a thing you inhabit. It is a process you participate in. Some thinkers have compared this to a simulation, not in the sense of a computer rendering graphics, but in the sense of a system that resolves detail only when required. Others describe it as a participatory universe, where observers are not accidents but essential, components. John Wheeler, one of the architects of modern physics, suggested that the universe may be self-observing, that the act of observation is not something that happens inside the universe, but something the universe does to itself through conscious beings. This idea is unsettling because it collapses the distance between subject and object. You're not merely in the universe, you are part of how the universe becomes real. This does not grant special powers. It does not mean thoughts rewrite physics, but it does imply that existence is relational, that reality is something that emerges between systems, not something imposed from above. In such a universe, certainty is always provisional. Facts exist, but only within contexts. Truths are real, but not absolute. They depend on how, where, and by whom they are observed. This challenges the comforting idea that there is a single hidden layer of reality beneath appearances, waiting to be uncovered. Quantum mechanics suggests there may be no final layer, only deeper relationships, only more refined questions. The universe may not be a finished answer, it may be an ongoing conversation. And if that is true, then existence itself is not about uncovering a predetermined truth. It is about participation, about interaction, about the continuous act of turning possibility into experience, which leads to the final unavoidable question. If the universe becomes real through observation, who or what is it ultimately observing itself through? the question the universe is still asking. After everything quantum physics has revealed, one truth remains unsettlingly unresolved. The universe does not behave like a closed book. It behaves like a question that never fully stops being asked. If reality requires observation to become definite, then the universe is not merely unfolding in time, it is responding. Each interaction sharpens a blur into a fact. Each measurement forces a choice. Each observer becomes a point where uncertainty gives way to experience. But this raises a final haunting problem. Observation cannot be removed from the story. No matter how far physics pushes the boundary, detectors observing detectors, environments collapsing systems, universes branching endlessly, the question simply moves one step back. At some level, something must register what has happened. Something must experience a result rather than remain suspended in possibility. The universe, it seems, is structured around this requirement. This does not mean there is a single watcher behind the curtain. Quantum mechanics offers no evidence of a cosmic eye. What it suggests instead is more unsettling. That observation is not an external act imposed on the universe, but an internal process the universe performs through its own complexity. Stars form, chemistry emerges, life appears, minds awaken, and through these minds, the universe gains the ability to observe itself with increasing resolution. In this sense, consciousness may not be an accident. It may be a phase transition, a point where the universe becomes capable of asking what it is doing. This reframes the old question of existence. The universe may not be striving toward an answer. It may be sustaining a dialogue, a feedback loop between possibility and awareness, where reality is continuously refined through experience. The past is stabilized by present observation. The present is shaped by interaction. The future remains open not because it is unknown, but because it is genuinely undetermined until the universe commits. Reality, then, is not a destination, it is an ongoing act. And perhaps this is why the observer problem never resolves cleanly. Because it is not a bug in the theory, it is a mirror. It reflects the fact that we are not standing outside reality trying to describe it. We are embedded within it, participating in its formation simply by being here, asking questions, seeking patterns. The universe does not offer a final objective story that exists without witnesses. It offers consistency through interaction, meaning through relationship, existence through experience, and as long as observation continues, as long as something somewhere is capable of asking, measuring, noticing, the universe will continue to answer, not with certainty, but with reality itself.